For nearly a century, one of the greatest debates in physics remained unsolved. Albert Einstein versus Niels Bohr. Determinism versus quantum uncertainty. Particle and wave duality versus fundamental complementarity. Now in 2025, the International Year of Quantum Science and Technology, two research teams have provided the most definitive answer to this debate yet. Using technologies Einstein and Bohr could never have imagined, they resolved the debate, and Einstein was wrong. Let's now explore how they achieved this, what it means for our understanding of reality, and why this century-old debate is still important for tomorrow's quantum technologies. The story begins at the Fifth Solvay Conference held in Brussels in 1927. The world's greatest physicists gathered at this conference to discuss the emerging theory of quantum mechanics. Einstein and Bohr were at the center of a philosophical conflict that would define how we understand nature at the smallest scales. The disagreement centered on a concept called complementarity. This concept implied that certain properties of quantum particles could not be defined simultaneously. Bohr argued that this was not a limitation of measurement technology. It was a fundamental property of reality itself. A quantum system arranged to exhibit particle-like properties cannot simultaneously exhibit wave-like interference. These are not two incomplete definitions waiting to be reconciled. They are mutually exclusive aspects of how quantum systems behave, and nature forces you to choose which one to measure. Einstein rejected this view. He believed quantum mechanics was incomplete, and that deeper deterministic laws were hidden beneath its probabilistic surface. He argued that if we were clever enough, we could observe both wave and particle behavior simultaneously. Einstein proposed a thought experiment, Gedanken experiment, that he believed would expose a flaw in Bohr's principle of complementarity. The setup of the experiment was deceptively simple. Consider the famous double-slit experiment, which produces an interference pattern, proving the wave nature of individual photons. Place an extremely sensitive scale at each slit that can detect the small recoil produced when a photon passes through. Einstein argued that by measuring this recoil, you could determine which slit the photon used without disturbing it. Particle behavior yields path information. Wave behavior yields interference. Both can be seen simultaneously. Complementarity is violated. Bohr said the uncertainty principle would make such measurements impossible. Any device sensitive enough to measure the slit's recoil would become too uncertain to obtain clear interference. Bohr insisted that the universe did not permit what Einstein proposed. For decades, this remained a theoretical speculation. The experiment was too sensitive and required controlling individual atoms and photons in ways technology could not achieve. Until now. In July 2025, a team at MIT led by Wolfgang Ketterle turned Einstein's thought experiment into physical reality. Ketterle, who won the Nobel Prize in 2001 for creating Bose-Einstein condensates, designed a device that replaced physical slits with individual atoms suspended in space by laser beams. His team cooled over 10,000 rubidium atoms to just 1/1,000,000th of a degree above absolute zero and arranged them in a crystal-like optical lattice where each atom was separated by only 1/10 of an inch. These ultra-cold atoms became Einstein's moving slits. When a photon scattered off an atom, the atom recoiled slightly, as Einstein predicted. Crucially, however, the team could control the amount of scattering information by adjusting the quantum uncertainty of each atom's position. A tightly confined atom had a well-defined position and scattered very little, supporting wave interference. A loosely confined atom allowed measurable recoil, revealing which path the photon took and eliminating the interference pattern. The results are clear. Lead author Vitaly Fedosov and colleagues observed a smooth and continuous balance. When the atom's position was uncertain and the recoil was immeasurable, the interference fringes appeared strongly. As the position became better defined and the recoil became detectable, the interference pattern gradually faded. There was no regime where both were fully present. The relationship followed the curve predicted by quantum mechanics exactly and confirmed Bohr's complementarity with extraordinary precision. Most importantly, the MIT team addressed Einstein's specific suggestion about mechanical breakdown. To prove that the laser trap did not behave like a spring, they conducted additional experiments where they turned off the lasers after each photon interaction. The atoms floated freely for microseconds before gravity pulled them down. Even without mechanical support, the results remained the same. What mattered was not the presence of springs or supports. What mattered was the quantum entanglement between the photon and the atom. When a photon interacts with an atom, the two become entangled. Information about the photon's path is encoded in the atom's quantum state. When this information exists anywhere in the universe, even if no conscious observer reads it, the phase relationships necessary for interference disappear. This process, called decoherence, does not require measurement or awareness. It occurs when the quantum system becomes associated with something that can, in principle, distinguish between alternatives. Independently, a team in China reached the same conclusion using a different experimental approach. John Wei Pan and colleagues from the University of Science and Technology of China, internationally known as the father of quantum, captured a single rubidium atom using optical tweezers. Optical tweezers are essentially a focused laser beam that behaves like the tractor beams in science fiction films. This atom acted as an ultralight beam splitter, and the momentum quantum of the photon became entangled with the momentum of the photon before encountering the double slit. Pan's team controlled how much path information was encoded in the atom's movement by adjusting the electromagnetic fields. Again, they observed a strict trade-off. More path information meant less interference visibility. This relationship was quantitative, precise, and as predicted by quantum theory. Einstein's hope that intelligent design could preserve both features simultaneously was proven fundamentally impossible. What made these 25 experiments particularly powerful was their adjustability. Previous complementarity tests typically produced discrete yes or no results by turning detectors on and off. Teams from MIT and China were able to continuously vary how much information was present, creating a smooth transition between wave-dominant and particle-dominant regimes. This allowed them to quantitatively measure the relationship between interference visibility and path distinguishability, confirming the mathematical structure of quantum mechanics with unprecedented detail. The implications extend far beyond resolving a historical debate. These experiments provide a new tool for understanding decoherence, the process that causes quantum systems to behave classically. Quantum computers rely on interference between different quantum states to perform computations. Unwanted path information leaking into the environment causes decoherence and eliminates the computational advantage. The ability to precisely control and measure how information loss affects coherence is crucial for improving the stability of quantum bits and error correction. Quantum cryptography faces similar challenges. Secure quantum communication works because any attempt to measure the quantum signal inevitably alters it. The trade-off demonstrated in these experiments, where obtaining path information reduces interference, forms the basis of this security. As quantum communication networks expand, fully understanding how information and coherence interact becomes critical to maintaining security guarantees. The Chinese team has announced plans to extend their devices to more complex systems involving multiple atoms and photons. By studying how entanglement and decoherence interact in larger networks, they aim to understand how quantum information propagates and degrades. This has important implications not only for quantum technologies, but also for fundamental physics, including theories attempting to unify quantum mechanics with gravity. Perhaps most striking is the symbolic timing. The United Nations has declared 2025 the International Year of Quantum Science and Technology to mark the centenary of quantum mechanics revolutionizing physics. Einstein and Bohr's debate took place just 2 years later, in 1927. Now, nearly a century after this famous clash, technology has advanced to the point where it can perform the experiment Einstein proposed with extraordinary precision. The result fully vindicates Bohr's position. Complementarity is not a temporary limitation waiting to be overcome with better tools. It is a fundamental feature of quantum reality. Wave behavior and particle paths cannot coexist in the same physical system because the quantum state does not allow it. Information is a physical quantity, and the universe imposes strict limits on what can be known at the same time. Einstein's statement, "God does not play dice with the universe," is famous. Quantum mechanics proved him wrong on this point. Now these experiments are proving him wrong on complementarity as well. However, Einstein's mistakes advanced physics. His challenges forced clearer thinking, better experiments, and deeper understanding. What began as a philosophical debate in Brussels has become a practical research tool investigating the structure of quantum reality with single atoms and single photons in Cambridge and Hefei. The century-long debate has ended, but the questions it raised about reality, measurement, and the nature of knowledge remain as relevant as ever. However, we now use these answers to build tomorrow's quantum technologies.